Now that we talked about sequences of functions, it's time to discuss series of functions. And the generalization from regular series is going to be fairly straightforward in terms of a definition. So suppose that fn of x is a sequence of functions that are all defined on some interval I. So then, of course, we can consider another sequence of functions also defined on I. And I'm going to define these functions, these new functions, in the following way. Gk of x is going to be the sum from 1 to k. Later on, the lower limit can be anything, can be 1, can be 2, can be 0, but just for the purposes of this definition, let's use 1 of fn of x. Right, so if all functions fn of x are defined on I, then there's some of the first k functions like this is also well defined on I, so it has I as its domain. And so we got a sequence, right, because for each k, a function like this can be defined. So for larger k, you add more and more of these functions fn of x. So then what we would like to do so we can consider another sequence and then we can study the limit of gk as k goes to infinity. So limit of gk as k goes to infinity, right? If this limit exists, then we would say that a series sum n from 1 to infinity fn of x converges. So you see that this definition is basically exactly the same as the definition that we're used to for the regular series. So basically, if you want to add up infinitely many terms of your sequence, what you do, you add finitely many elements to form a partial sum. And in fact, maybe let me change annotation here a little bit, because partial sum is better denoted by s. So sk now is a function, and so if I take a limit as k goes to infinity, all these functions, I should be able to, and the limit exists, then I will should be able to say that the series of functions converges. Okay, so it's all nice and good, except for one thing. Remember that for numbers, convergence was really simple, right? Really simple in a sense that we had the definition of a limit. If a limit exists, then we're happy. Then a series, if a limit of partial sums exists, then your series converges. But as we discussed in the last couple of lectures, for sequences of functions, convergence is more complicated. In fact, we were able to determine define two types of convergences. One type was a pointwise convergence, where you fix individual x and then you study convergence of fn of x at that given point. And then there was also uniform convergence, where the distance, the supremum distance between fn and f, right, went to 0 and then went to infinity. So in this case, we also can have two different convergences. Two choices. Choice number one. If I should write it here. If Sk converges pointwise on I, then we would say that the series sum and from 1 to infinity of fn of x also converges pointwise. And if Sk converges uniformly on I, then of course we would say that the series converges uniformly, right? So two types of convergences. Okay, let me fix this. So if the sequence of partial sums converges uniformly on I, then we would say that the series converges uniformly on I. Okay, and so the question in this and next section is going to be always related to this fact, what kind of convergence of our series we do expect. And depending on the type of convergence, you would expect that the properties of a limit of a series might change. Okay, so, but for now, let's talk about pointwise convergence. And in fact, again, for now, let me talk about a particular kind of series, and that's a power series. So if fk of x above, right, is equal to ak times x minus x0. In fact, we're using n, so let me switch to n. If fn of x is equal to an x minus x0 to the power n, so then the series sum from 1. In fact, here I'm going to start from 0. From 0 to infinity, fn of x is going to look like a series n from 0 to infinity an x minus x0 to the power n, and this is going to be called a power series. That is centered at x0. Now, here, an, right, which you can think of as a sequence. So an is a sequence of infinitely many numbers. These guys are called coefficients of your power series. All right, so I hope this makes sense, and in fact this is stuff that you already have seen in regular calculus. Now a couple of points that I want to make here. So let's note the following. Note that partial sums of a power series that are, of course, equal to the sum and from 0 to k of an x minus x 0 to the power n. They're all polynomials in x, right? And the observation that we can make, so in fact, they're all polynomials in x, and therefore the domain of sk is the set of all real numbers for all k, right? So all possible partial sums of a power series are polynomials. Polynomials of increasing degree, right? K gets bigger, the power gets bigger. So at least formally, we can think of a power series as a polynomial that has infinite degree. Of course, that by itself doesn't have any meaning, but as long as the sum of the power series is defined, then at those points you can sort of think about the function as a polynomial of infinite degree. Anyhow, so now the next question is, if I have a power series, what is the domain of the power series? And we're already fully equipped to answer this question. Power series, after all, is just a power series, is just a series, right? And for series, we already know what sort of techniques we can employ to figure out if a given series converges or not. So let's see, what exactly do we need to do to discover if the power series would converge or not, so at which x the power series would converge. And those x will then form a domain of a power series. So what sort of tools can we use to figure out if the power series converges or not? And again, at this point, I'm discussing pointwise convergence. So domain of the power series then is going to consist is equal to the set of all points on the number line where the series converges, right? Where the series. Let me copy this. So where the series converges. Okay, so now I want to decide where converges pointwise. So to determine these points, what do we do for the pointwise convergence? Fix any x in R, right? And then study the convergence of and study convergence of a series of numbers. Which is exactly the same as the series above, right? Except that now x is a fixed number, x0 also is a fixed number. So it's just a series of numbers. So copy, paste with x fixed. And the method that we can use to determine convergence is, for example, a root test, right? So let's say we're going to use a root test, and remember from Advanced Calc 1 that the root test is weaker, right? So root test can be used for a larger possible set of series, right, than the ratio test. Sometimes root test will be conclusive, while the ratio test is not going to be conclusive. We provided examples of that back in Advanced Calc 1. So I'm going to use a ratio test. And what does the ratio test require me to do? In principle, again, if ratio test is too complicated, then of course we can use, if I was said a root test and I written a ratio test. So here I'm going to use a root test, but in general, ratio test is as efficient as a root test in most cases. So in practice, we will use either one. Okay, so but in this case, so what do I need to do? I need to take a limit as n goes to infinity of the n plus first term of my series divided by the nth term of my series. What is n plus first term? It's an absolute value of an x minus, actually n plus first over n, so n plus first term, an plus 1 times x minus x0 to the n plus 1 divided by the absolute value of the nth term, an x minus x0 to the power n. So let's see, what is this? This can be simplified. And again, I'm saying root test, but I'm writing a ratio test. I'm sorry about that. Let's go back to the root test. So this would be nth root of the absolute value of the term of a series. to the power 1 over n. And in fact, the most general version of the root test that we discussed was a version where we're taking lim sup. Okay, so what is a lim sup here? It will be a lim sup n goes to infinity. And then we can distribute the absolute value inside the nth root. So absolute value of an times x minus x0 to the power n, I can write as absolute value of an times x minus x0 to the power n, the whole thing to 1 over n. And this, we can now simplify it further. This is the same thing as lim sup n goes to infinity of absolute value of an to the power 1 over n, and then times x minus x0 to the n to the power 1 over n. Powers will cancel, and this is just x minus x0, right? Now, when I'm taking my lim sup, everything is positive here, and so x minus x0 is a constant, so I can take a positive constant outside of lim sup. Remember that if it's a negative constant, you cannot do it, but for a positive constant you can. So this is x minus x0 absolute value times lim sup n goes to infinity absolute value of an to the power 1 over n. And then for the sequence of numbers an, this limit is just some number, right? So this guy is some number in R. And in fact, we can denote it by something, let's call it alpha, right? So then what we got is alpha times x minus x0. And what is the root test? The root test requires this number to be less than 1 for the series to converge absolutely. So if this number is less than 1, then the series converges absolutely, and otherwise it diverges. I'm going to be not very careful now. It will diverge if this number is greater than 1, and when the number is equal to 1, remember that the test is inconclusive. But what is important is that I can guarantee that the series converges when alpha times x minus x0 is less than 1. And so then the final conclusion here, if I solve this inequality for x minus x0, I get that x minus x0 must be less than 1 over alpha. And so this inequality describes the set of all x for which the series is going to converge, right? So if my fixed x is such that magnitude of x minus x0 is less than 1 over alpha, right? And the alpha, again, is less lim sup. It's some number that depends on the coefficients of my power series. So if x minus x0 is less than 1 over alpha, then the series converges absolutely. And otherwise it does not converge, except possibly of the situation when x minus x0 is equal to 1 over alpha. But again, this will be looked at separately. Okay, so then we have three choices. And what I'm doing here in the book is formulated as a theorem. So in a sense, I'm proving a theorem before I stated it. And I'm not going to state it, you just look in the book. So here I'm simply going to discuss possibility of how the domain of the function of the power series can look like. So we have three choices. Number one, what happens if alpha is equal to, let's see, what can alpha be? If I'm taking lim sup of some sequence, then remember we discussed that lim sup can be a finite number or it can be infinity. In fact, in this case, you're taking lim sup of a non-negative sequence, an to the power 1 over n. So that means that lim sup, the lowest it can be 0, and the highest it can be is infinity. If lim sup is equal to 0, right? So first case, alpha is equal to 0. Well, then my division here doesn't make sense, right? Because 1 over 0 does not make sense. But 1 over 0 is kind of like infinity. Regardless, if I look at where this inequality came from, it came from here. If alpha is equal to 0, then really it doesn't matter what x minus x0 is. The left-hand side of inequality is 0, and it is always less than 1, then regardless of what x is. So then this means that I can conclude that my series is going to converge regardless of what x is. So it converges for all x. So formally at least, I can write sort of that x minus x0 is less than infinity, so it can be arbitrarily large. And so then the series converges for all x in R. Okay? Number two, alpha is equal to a finite number, right? Then, or in fact, let's just say it this way, alpha is finite. If alpha is finite, then x minus x0 is less than 1 over alpha, and that is the same thing as saying minus 1 over alpha is less than x minus x0 less than 1 over alpha. Or, again, this is the same thing, x0 minus 1 over alpha is less than x less than x0 plus 1 over alpha. Okay, and then number three, alpha can be equal to infinity, right? If I take lim sup, it's entirely possible that lim sup is infinity. Then again, formally, if I look again at the inequality that I got here, if I have 1 over infinity, that must be 0, right? Well, so let's look at the original equality. If alpha goes to infinity, then if x is not equal to x0, x minus x0 is a positive number, alpha goes to infinity times positive number still goes to infinity. Infinity is not less than 1, so it means that for any x, the for any x, the series is not going to converge, except for one case. If x is actually equal to x0, right, then alpha times x minus x0 is 0, 0 less than 1, so the series converges. So when x is equal to x0, the series converges. When x is not equal to x0, the series diverges. Then, so in this case, the series converges. Only when x is equal to x0. Okay, so what can we observe from this? So it is possible that the series converges for all x, or I can go from x0 up or down by any amount I wish. Or I'm in a situation number 2, when I can go from x0 up or down by 1 over alpha. Or I'm in a situation 3, where I can only go from x0 up or down by the amount 0. So then we'll use the following terminology, because we can go from x0 up or down by the same amount in all 3 cases. So then we'll say, so we say that the radius of convergence you sort of pretend that the symmetric interval around x0 is sort of a one-dimensional analog of a circle. So its radius then is going to be what? Infinity in case number 1, right? Because you can go up or down by an infinite amount. So in case 1, r is infinity. In case 2, radius of convergence is 1 over alpha. And in case 3, the radius of convergence is going to be actually 0. So those are your all possibilities, right? You only have 3 possibilities. Either you always have a symmetric interval, but it can either have infinite, finite, or 0 radius of convergence. All right, so that's what we know about the power series. So the power series can would always converge in a symmetric interval, but its radius does not have to be infinity. So even though, as we said, the partial sums of a power series are all polynomials defined everywhere on the real line, when k goes to infinity, the resulting sum of the power series is not defined everywhere, but it's only defined on the radius of convergence, or on the interval of convergence, right? I did not actually make this definition, but I will simply say it in words. So the domain of a series is going to be called an interval of convergence, and interval convergence is always centered at x0. And that's the reason why x0 is called the center of a series. Okay, so then we are ready to do several examples here. So example number 1. I'm going to consider the series the power series sum and from 0 to infinity of x to the power n. Right, so for this power series I know that, not xn, but x to the power n. For this power series I know that all coefficients of the series are 1. And actually what distinguishes 2 different power series is a set of coefficients, an, right? So in this case, all an's are equal to 1. And the question is, where does this power series converge pointwise for which values of x? We have two choices. Either we, again, use root or ratio test, or we simply examine this series and we know so that any series that looks like the term of which looks like a times r to the power n, this thing is a geometric series, right? So it's a geometric series here. And it's a geometric series with a multiplier x, right? Because I have x to the power n. So that means that each next term of the series is a previous term times x. And because it's a geometric series with a multiplier x, it would converge as long as the multiplier in absolute value is less than 1, right? So this thing converges if x is less than 1, otherwise it diverges. So then the radius of convergence here is 1. And the interval of convergence right, we just rewrite absolute value of x less than 1 without using absolute value sign, and we get minus 1 less than x less than 1. We can actually say more in this case. So further, for the power series, I actually know exactly how the sum of its series looks like, right? So sum of from 0 to infinity of x to the power n. If you remember, the sum is equal to the first element of the series. When n equal to 0, that first element is x to the 0, 1, divided by 1 minus x. So this is a formula for the sum of a geometric series. And the interesting thing about this formula is, so let's write this as a note, the domain of the power series, again, minus 1, 1, right? While the domain of 1 over 1 minus x is all x except for x equal to 1, right? So I can write this r minus the point 1. So the domain of the function 1 over 1 minus x is much larger than the domain of the power series. How come? The reason is that the sum of the series is equal to 1 over 1 minus x only when the series converges, right? So, and the series only converges here. So the domain of the power series is not the entire domain of 1 over 1 minus x, but it's only a part of that domain. Which I hope makes sense, right? Because the power series converges only in a subset of the domain of the function that forms its sum. Okay, so that is example number 1. Let's do example number 2, same question. And now what I want to consider is the following series. Sum. By the way, I forgot to mention or draw your attention to it. So in this case, not only the coefficients are 1, but the series also is centered at 0 because there is no x0, right? I'm not using x minus x0 to the power n, but just x to the power n. Let's do the same thing here. Sum from 1 to infinity, but now of x to the power n divided by n. So what happens in this case? This is no longer a geometric series. So to determine its convergence, pointwise convergence, I need to use either the ratio test or root test. In this case, because I have just n on the bottom, it's easier to use a root test. So use the ratio test. To determine pointwise convergence. All right, so what do? We take a limit, in principle lim sup, but because in this case these are power functions, it's just algebraic functions, we just need to, okay, I forgot what I was going to say. So we're going to use a ratio test. Because we don't need to use a lim sup, because in this case limit would exist. So limit as n goes to infinity. N plus first term, absolute value of n plus first term is x to the power n plus 1 divided by n plus 1. We're dividing this by the nth term, so absolute value of nth term, x to the n over n. Now what's that? This is a limit as n goes to infinity. Only x here can be negative, so I'll put the absolute value around x. So x to the n plus 1 over n plus 1 divided by x to the n, absolute value of x to the n. And because I'm dividing by n, dividing twice by n, I have n on the top. Well, x to the n I can cancel out. And so then this should be a limit n goes to infinity, absolute value of x, n over n plus 1. Absolute value of x is a constant, which I can pull out. And I have a limit when n goes to infinity of n over n plus 1 left. And we looked at these limits before, right? When n goes to infinity, the limit of the ratio of two powers is just the limit of the largest power on top divided by the largest power on the bottom, or 1 is negligible compared to n on the bottom, or we can divide top and the bottom by the highest power of n, which is n in this case. If you do any of these, essentially with n is large, you have n on the top, n on the bottom. Limit of the ratio is 1. You have absolute value of x there, so absolute value of x is the limit. And the series is going to converge as long as the limit is less than 1, right? So that means from here, the radius of convergence is equal to 1, and the interval of convergence so far is from -1 to 1, right? because that's what absolute value of x being less than 1 means. Well, but remember that we have one issue. So if absolute value of x is greater than 1, then for sure the series does not converge. But when absolute value of x is equal to plus or minus, is equal to 1, or x is equal to plus or minus 1, then the ratio test is inconclusive, and we have to test the endpoints separately, right? So I need to test the series at x equal to plus or minus 1 using some other method. Or another test. Okay, so let's look at x equal to 1 first. If x is equal to 1, how does my series look like? It looks like sum and from 1 to infinity of 1 to the n over n. But 1 to the n, of course, is 1, so this is sum from 1 to infinity of 1 over n. Well, what do I know about this series? It's a harmonic series, so it's diverges. So diverges. What about x equal to minus 1? If x is equal to minus 1, then we have a sum n from 1 to infinity of minus 1 to the n over n. And what is that? That's an alternating series. When does the alternating series converge? When without minus 1 to the n, in this case 1 over n remains, if that sequence 1 over n decreases, monotone decreasing, and goes to 0. And clearly 1 over n is monotone decreasing and goes to 0. So this series then converges by the alternating series test. And so, therefore, the full interval of convergence is going to include minus 1. Okay, and that takes care of this example. Now, the final example is going to be this one. Sum n from 0 to infinity, x to the n divided by n factorial. So once again, this is not a geometric series, so it's a power series. It's not a geometric series, so I have to use ratio or root test. Presence of n factorial suggests that I need to use the ratio test. Okay, so then we need to take a limit. N goes to infinity. Again, absolute value of x to the n plus 1 over n plus 1 factorial divided by x to the n over n factorial, right? Immediately, I can get rid of x to the n, right, just by canceling. So this is a limit n goes to infinity. X is the only thing that can be negative, so absolute value of x, n plus 1. Well, n plus 1 factorial, by the way, is actually n factorial goes on the top, so sorry. Because it's a ratio which is sitting in the denominator, so it's x to the x times n factorial. And in the denominator, we should put n plus 1 factorial, but what is n plus 1 factorial? It's product of all integers up to n plus 1, so I can write it as n factorial, product of all integers up to n times n plus 1. So n factorial goes away. And therefore, I need to take a limit. Remember that we're looking at the piecewise convergence, so x is a fixed number. So absolute value of x is a fixed number. So when n goes to infinity, fixed number over n plus 1 certainly goes to 0. So this is 0 for all x, so it's less than 1 for all x in R. So therefore, radius of convergence is infinity, and the interval of convergence is an entirely real line. All right, so one last thing to mention here. So if I look back at the example of a geometric series, there I knew exactly what the sum of the series looks like. It's 1 over 1 minus x. And certainly 1 over 1 minus x is a continuous function on the interval from minus 1 to 1, right? When 1 is not included. For example 2, I already don't know what the sum of the series looks like. I know that the interval of convergence is from minus 1 to 1, but how does the sum of the series look like? I have no idea. And if I'm interested in the question, does the sum of a series, so sum of a series is going to be a function defined on the interval from minus 1 to 1, but if I'm interested in whether this function is continuous or differentiable, at this stage, I cannot really say anything, right? Because I'm just adding infinitely many functions. How can I know if a limiting function is continuous or not? Same deal in the last example. I know that this function, right, which is the sum of a series x to the n over n factorial, I know that this series is defined at all points on the real line because I proved convergence at all points on the real line. But how nice that function represented by the sum of the power series is, whether it is continuous and or differentiable, that I don't know. So I need to invent some new tools to determine the properties of a sum of a series of functions, and we're going to return to this question in the next lecture.